we will discuss other linear classifiers that does not use neural network representation. Such linear classifiers can be more powerful than the perceptrons and easier to implement. However, some of them do not have the ability to learn nonlinear functions unlike deep neural networks. The first linear classifier that we will discuss is the sum of squared errors classifier. For this classifier, let us have a training set of m feature vectors and their true class labels y. We can use a vector of weights w and the bias parameter to find the decision boundary that is expressed in terms of an extended feature space x star, where we combine all the features and the last value is 1, and we will multiply this with a weight vector with some weights and bias term, just like perceptrons. For this purpose, we will estimate a vector of parameters w star in the extended feature space x star to find the decision boundary that is w star transpose x star equals to 0 using the squared errors, where the estimate for the class labels is y hat, which is w star transpose x star. The cost function then becomes jw star is the quadratic cost function, where we subtract the true class labels from the estimated class labels and take the square of it. When we take derivative of the cost function, we have this expression. Since here we can replace w star transpose xi star with xi star transpose w star, the expression becomes let's expand this expression. So from I equals 1 to m, we have xi star times yi minus xi star, make this replacement so that xi star transpose and w star equals to 0. Here we can create a feature matrix that is x by stacking up all the feature vectors that we use for training. For example, in the first row we have the first extended feature vector. In the second row we have the second extended feature vector. In the mth row we have the mth extended feature vector, and we can use this feature matrix to create a better representation of this this equation 1. Okay, so when we replace the second term here with x transpose x, because we have the summation here, and since we have defined x so that we can represent this summation by using this expression, and we can represent this summation by using this expression, the equation 1 becomes x transpose x w star equals x transpose y, and we can find the feature vectors, we can find the values for the extended weight vector by solving this equation. How do we solve it? It's simple. We can simply get the inverse of this x transpose x matrix and multiply it with this side, and we get w star vector, where x transpose x minus 1 times x transpose is also called pseudo inverse of a non-square matrix, since our feature matrix is most likely to be non-square. As an example, let us consider a two-class problem where the feature vectors are two-dimensional. Let us find the classifier parameters for the sum of squared errors classifier. The feature vectors for the first and second class are given below. So these are the feature vectors for the first class. These are the feature vectors for the second class. The solution is by the above method which we have shown. So let us first create the feature matrix X. For that purpose, we just take this feature vector, write like this, and as a last column we type 1 because we will be multiplying this bit with the b parameter. As the second row we have this. As the third row we have this. And for the class labels, for the class 1 we have +1, and for the class 2 we have -1 as their class labels. So we can then calculate x transpose x, which is this, and x transpose y, which is this, and we can take the inverse x transpose x to the -1, and we can easily calculate the parameters for the decision hyperplane. That's w star, which is x transpose x to the -1 times x transpose times y. We have calculated these. So we have calculated here, and we have calculated this part here. By using this extended weight vector, we can then estimate the class label of a new sample, unknown sample u, by getting the sign of the this expression, where we just type w transpose times u, and that's all. Thank you for listening.